Every day, quietly, millions of fish are changing the way the world eats. Not in nets out in the ocean, but inside high-tech farms controlled by sensors, algorithms, and screens filled with data. And among all those fish, one has become the undisputed star, Tilapia. A mild-tasting fish, cheap, consistent, and produced at such a massive scale that it now competes head-to-head with salmon and tuna as a daily protein in many countries. And there is one place that dominates this industry like no other: China. Their enormous farming systems, from traditional ponds to closed farms with water recirculation and digital control, produce hundreds of thousands of tons of tilapia every year. This is no longer just aquaculture. It is a precision industry where every degree of temperature, every gram of feed, and every liter of water has a direct impact on the profitability of the business. But here is what is truly interesting for you. Behind every tilapia fillet that reaches the supermarket, there is a complete chain of technical and financial decisions. How much does it cost to raise 1 kilo of tilapia? What technologies make it possible to reduce that cost? What are the real margins of a modern producer? And to what extent can this model be sustainable and profitable at the same time? Welcome to Complete Process, the channel where we open the doors to the industries that feed the world. In this documentary, we are going to walk step by step through China's tilapia production chain, from genetics and hatcheries to intensive farms, harvesting, industrial processing, and the business behind export. A journey to understand not only how this fish is raised, but why it has become one of the most important aquaculture businesses on the planet. Everything starts long before you see a single fish swimming. The first link is in the breeding centers, the genetic laboratories of tilapia. There, they do not choose a male and a female at random. They work with genetic lines designed for 3 very clear goals: fast growth, good feed conversion into meat, and resistance to disease. To achieve that, they combine years of traditional selection with modern genetic analysis tools. The brood stock live in separate tanks, with filtered water and very tightly controlled parameters. They are fed high-quality diets. Their health is monitored, and everything is recorded: how fast they grow, how often they get sick, how many eggs they produce. Only a small fraction of these fish is considered elite and is used as the foundation of the breeding populations. This not only improves productivity, it also reduces economic risk. A fish that grows faster and gets sick less is in the end a more profitable business. When the females lay their eggs and fertilization occurs, many tilapia species do something surprising. They protect the eggs in their mouths, a behavior called mouth brooding. On farms, however, much of this process is managed in a controlled way. The eggs are collected and moved to incubators where temperature, water flow, and oxygen are kept constant. Each tray of eggs is, in practice, a small investment the farm will protect in order to turn it into thousands of marketable fish months later. When the larvae hatch, they move into nursery tanks. Here, the key factor is survival. These are tiny fish, extremely sensitive to any change. The water is kept crystal clear, the temperature stable, and oxygen levels always high. Air blowers, filters, and constant exchange systems are used to prevent spikes in ammonia or nitrites. Feed rations are small but frequent, using high-protein microdiets that allow accelerated growth in a short time. And here comes our second hook, right when it seems like we are only talking about biology. In the most advanced farms, it is no longer a technician with a stopwatch deciding when and how much to feed. It is intelligent systems. Sensors and cameras observe fish behavior and, with the help of algorithms, adjust doses in real time. If the fish eat too slowly, the system reduces the ration to avoid wasting feed. If the group reacts with high energy, it slightly increases the dose. Every fine adjustment translates into lower feed costs and less water pollution. And in an industry where feed can represent up to 60% of production cost, that detail is the difference between earning well or barely surviving. When the fish reach fingerling size, it is time to decide where they will complete their growth. And in China, that world is divided, broadly speaking, into two models. The first is traditional earthen ponds located in rural areas. These are large water surfaces fed by rivers, canals, or reservoirs. The technology here is simpler: mechanical aerators, fertilization management, visual control of water color, and feeding adjustments based on the producer's experience. It is a model that requires a lot of land, labor, and a good water source, but it has relatively low initial costs. The second model is recirculating aquaculture systems, known as RAS. Here, water is hardly wasted. It circulates in a closed loop that passes through mechanical filters, biological filters, disinfection systems, and oxygenation tanks. With this type of technology, you can produce up to 4 times more tilapia per cubic meter than in a traditional pond, using a fraction of the water. In addition, parameters are controlled from a monitoring room. Oxygen, temperature, pH, flow rate, and fish density are displayed on screens in real time. The economic difference is very clear. A traditional system depends on the weather, available water, and the producer's eye. A RAS system requires a much larger initial investment in infrastructure and technology, but it offers 3 key benefits: more kilos produced in the same space, more stable production throughout the year, and the ability to locate near urban centers or processing plants, reducing logistics costs. For an exporting company, that stability and predictability is often worth more than the savings from a lower initial investment. Meanwhile, the fish keeps doing what it does, eating and growing. Tilapia has another very important competitive advantage: its diet. Unlike carnivorous fish like salmon, which require fish meal and fish oils in their diet, tilapia can be fed on feeds based mainly on plant ingredients like soy, corn, wheat, and agricultural byproducts. That reduces dependence on capture fisheries and lowers feed formulation costs. For the producer, it means a more competitive feed cost. For the planet, less pressure on the oceans. In modern farms, every batch of tilapia has a production life record. The stocking date, initial size, stocking densities, feed types, and feed conversion ratios are recorded. If a farm manages, for example, to produce 1 kilo of tilapia with 1.4 kilos of feed, it has a clear economic advantage over another farm that needs 1.8 kilos of feed for the same result. That difference, multiplied by hundreds of tons, can be the line that separates a very profitable operation from one on the edge of shutting down. At the same time, health management is another key piece. Tilapia is relatively hardy, but in intensive systems, any failure can trigger bacterial or parasitic diseases. That is why strict biosecurity protocols are applied: controlled access to the farm, equipment disinfection, density management, quarantine for new batches, and constant monitoring of fish behavior. The global trend is clear: minimize antibiotic use as much as possible and focus on prevention, probiotics, vaccines where they exist, and proper water quality management. Fewer diseases means lower mortality, fewer losses, and the final product that is easier to sell in demanding markets. Up to this point, we have covered the biological and technological side, but this is agro-technology, so we also have to talk about business. In a typical cycle, the producer invests in fingerlings, feed, infrastructure, energy, and labor for 6 to 9 months. In the end, the margin depends on 3 things: how much feed was used per kilo produced, how much mortality occurred, and at what price the tilapia is sold. An efficient producer with low mortality and good feed conversion can reach attractive margins, especially if they sell to processing plants for export or manage to position themselves in higher value niches like certified tilapia, antibiotic-free tilapia, or tilapia raised in low environmental footprint systems. On the other hand, a producer with poor management, high mortality rates, and expensive feed purchases can end up working almost just to pay for the fish's food. That is why in China, and increasingly in other countries, there is a clear trend toward integration. Companies that control multiple stages of the chain, from fingerling production to processing and export. That integration allows them to capture more value at each link and reduce the risk of depending on only a few buyers. If you are enjoying this kind of analysis, where we don't just tell the technical process, but also the numbers and economic implications behind food production, I invite you to subscribe right now to Agro-Technology and turn on the notification bell. It is the best way to support this content, and make sure you don't miss the next documentaries about high-level agriculture, livestock, and aquaculture. Let's continue the tilapia journey. After several months in ponds or RAS systems, the fish reach market size, usually between 500 and 800 grams. At that point, the farm has already invested almost everything: feed, energy, time, labor. What happens in the next hours will determine whether the product reaches the market in optimal condition or loses quality and value due to failures in harvest and transport. In small farms, harvesting is done with nets and labor-intensive work. The pond water level is lowered, nets are pulled carefully, and the fish are concentrated into a narrow area where they are collected with dip nets or scoops. It is physical work that requires experience to prevent fish from suffocating due to lack of oxygen or injuring themselves by bumping into each other. Any extreme stress in this phase translates into softer flesh, higher mortality, and shorter shelf life. In industrial operations, harvesting becomes more technical. Large specialized fish pumps gently suction the animals and move them through pipes into oxygenated holding tanks. Some systems can harvest dozens of tons per hour, automatically coordinating pumping speed, water exchange, and loading into transport trucks. It is fine-tuned logistics. If the processing plant is ready to receive 50 tons that day, the farm adjusts its harvest to that volume. Not more to avoid overloading the cold room, and not less to avoid wasting factory capacity. The trucks that carry tilapia from the farm to the plant are usually equipped with oxygenation systems and sometimes sensors that monitor temperature and oxygen levels. Every kilometer traveled is a small test. Any failure in the system can reduce the quality of the entire batch. That is why many companies place their farms relatively close to their plants or develop aquaculture clusters, where multiple farms supply 1 or 2 major processors. When tilapia arrives at the processing plant, another value chain begins. First, the fish are kept in receiving tanks to stabilize them. Then stunning and bleeding are performed, complying with animal welfare standards and quality requirements. From there, the line splits into stations: descaling, gutting, filleting, trimming, inspection, washing, chilling, and packaging. Some plants rely mainly on skilled labor. Others have incorporated filleting machines capable of processing thousands of fish per hour with very uniform cuts. Tilapia can be sold in many forms: whole-gutted, skinless fillets, loins, frozen blocks ready to slice, even as raw material for breaded products or ready meals. Each format has its market and its price. For example, a premium fillet destined for a high-end restaurant or supermarket can be worth significantly more than a whole fish product intended for wholesale markets. This is where business strategy enters. Some companies choose volume and low costs. Others choose added value and specific niches. In high-end plants, fillets go through inspection systems that look for leftover bones, visual defects, or possible parasites. Metal detectors, X-ray systems, and high-resolution cameras are used. Then comes rapid chilling, or IQF, freezing, where each fillet is frozen individually to preserve texture and make later use easier. Finally, the product is vacuum packed, or packed in modified atmosphere, labeled with nutrition information, batch number, production date, and in many cases traceability data such as country of origin and production system. The resulting tilapia then travels to domestic or international markets. China exports a large part of its production to the United States, Europe, other Asian countries, and Africa. For the producer and processor, the key is managing logistics costs, exchange rates, and the sanitary requirements of each market. A container rejected at a port for failing to meet a specific rule can mean enormous losses. From a macroeconomic perspective, tilapia is a quiet engine. It creates jobs in farms, feed mills, processing plants, transport, logistics, and trade. In many rural regions, tilapia aquaculture has become a real alternative to traditional low-margin crops. The scalability of the business allows everything from small producers with a few ponds to integrated corporations, handling tens of thousands of tons per year. The risk, of course, is price competition. When the global market is flooded with cheap product, only the most efficient survive, or those who manage to differentiate. And now we reach the final element of this documentary: sustainability and the future of the business. On the positive side, tilapia has strong arguments. It is a fish that tolerates relatively high densities without losing too much performance. It can be fed on plant-based diets. It grows fast, and it adapts to different production systems. In well-managed recirculation systems, water use per kilo produced can be very low compared to traditional fishing or even other forms of animal protein production. However, there are risks that cannot be ignored. In poorly managed systems, nutrient-loaded effluents can contaminate rivers and lakes, triggering algal blooms and environmental problems. Excessive use of chemicals or antibiotics can create bacterial resistance and lead to rejection in markets. Uncontrolled farm expansion can displace other land uses or generate conflicts with local communities. The good news is that more and more tilapia projects are working with environmental certifications, integration with renewable energy, and circular economy models. Using sludge as fertilizer, integrating with hydroponic crops, installing solar panels over ponds to reduce evaporation and generate energy, and implementing more advanced water treatment systems. As consumers demand more information about what they eat, traceability and environmental guarantees become commercial tools as well. In the end, the story of tilapia in China and in the world is much more than the story of a cheap fish. It is an example of how technology, biology, and economics intersect to answer a massive question. How do we feed millions of people with quality protein, at affordable prices without destroying the environment. Every tilapia fillet you see in a supermarket is the result of decisions made in a genetics laboratory, in a control room of an intensive farm, in a processing plant, and in offices where costs, margins, and market strategies are calculated. Behind that fillet, there are oxygen sensors, feeding algorithms, recirculation pumps, microbiological analyses, refrigerated containers, and, of course, people who have made this fish their way of life. If this journey through the world of tilapia has helped you better understand how modern aquaculture really works and the business behind it, I invite you to hit like on this video, share it with someone who is also curious, and above all, subscribe to Agrotechnology and turn on the bell. Here we keep telling, calmly and in depth, the real stories behind what we eat and the technologies transforming the countryside, the water, and food production around the world. Tell us in the comments what other sector you would like us to analyze. Salmon, shrimp, chicken, beef, hydroponic crops, automated greenhouses. Behind each one, there is a chain of processes, machines, and economic decisions worth understanding. Thanks for making it to the end. This was Agrotechnology. See you in the next documentary.